Okay, so we are going to start off the unit of limits using graphs. So let's explore if we're given the function x cubed minus 8 divided by x minus 2. All right, so this, if you would graph it, would look like this shape. You'll notice there's going to be a hole at x equals 2 because that makes the original equation undefined. So what happens is we want to go ahead and substitute values if we were using a table that are really close to 2, okay? But right here at 2, it's undefined. So I'm going to go ahead and do that. Okay, so I went ahead and filled out those table values, and so this is what you'll notice. So as I get closer and closer and closer, when x is less than 2, but towards 2, we're getting y values that are closer to 12. And then as I'm getting closer to x equals 2, but from above, my y values are getting smaller and smaller and smaller, but they're also getting closer to 12. So what happens is we can't equal 12 exactly, but that is the idea of a limit, okay? So the limit of this function when x equals 2 is 12. All right, and so that's what the idea of a limit is. Think of it as a value that you are approaching, okay? So the way that we would write that is we would say the limit of f of x as x approaches 2 equals 12. All right, and then this is the notation. If we want to use the function, or we can actually write the function out. All right, so in order for a limit to exist, you must be approaching the same y value as x approaches some, I call it target C, from either the left or the right side, from smaller or larger, okay? If that doesn't occur, then that's when you would say that the limit does not exist, all right? And we just abbreviate that with D and E. So these are just some formal definitions to show the notation. Now, we're going to talk about one-sided limits. So the left-hand side, the one-sided left-hand limit, there's going to be this little exponent of a negative, and that means from below. So that means when you're smaller. So if we go up to this example, then I would be talking about these values. That would be the limit as x approaches 2 from below. Okay? And similar, the right-hand limit is from above, and there's a little exponent of a plus. And so that's when you're getting closer, but from bigger values. So this would be these values, and that would be the limit as x approaches 2 from above. Okay. It's not called a double-sided limit, but if there's no notation, then that means you need to compare the left and the right-hand limit. And if they both agree, then you say that the limit does exist. Okay? So it is important to understand that the limit value of 12 and the function value of the example we just did, they don't have to equal each other. Okay? All right. So let's look at some of these examples. Whoops. I'm going to make that a little bigger. All right, so let's say we take this graph. So I want the limit as x approaches 1 from below. So here's my target, and I'm going to approach it from the left side, and I'm looking for what the y values are going to agree upon as we get closer and closer and closer. So we got 0, 0.5, 0.9, 0.10. It's almost 1, even though it's not equal to it. They're getting closer to 1. All right, so that's your limit. And then let's go down here. The limit as x approaches 1 from above. So 1 is still our target, and we want to approach it from bigger. So like here's 2, 1.5, 1.1, and at 1. And so that y value, those are all approaching 2. So the limit as x approaches 1, well, since my left and my right don't agree, that's when you say D and E, does not exist. My function value at 1, we just go to the graph and we say, what is the y value? Well, the y value is right there, so that's 2. Okay? So just notice the difference between all the notation and what you're looking for on the graph. There really isn't any work to show. All right, let's look at this. The limit as x approaches 1 from below. So here's our target. And we're going to follow our graph from the left, and it's going to go up to y equals -1. Okay? and then 1 from above. So I'm going to go this way. As we get closer to 1, they're getting closer to y values of 1. Same thing, those don't agree, so we're going to say D and E. The function value at 1 is right here, and that's 0. Okay, see the difference? Let's try 2 more. The limit, here's our target, as 1 from below. Well, that's going to y equals 1, and 1 from above, y equals 1. Since my two y values agree, we're going to say the limit as x approaches 1 is 1. And the function of at 1, that is an open circle. That's just the way the program draws the graph. So we're going to say it does not exist. There's an open hole. All right, example 4. 1 from below, so here we go. So 1 from below, 1 from above, and they agree. My function value at 1 is right here. Okay. All right, so now we're going to talk about kind of some asymptotes. So when there's vertical asymptote, the technical limit does not exist because the idea of infinity really isn't a value that you're going to ever reach. But in terms of our limits, we are going to, it's a better description if you say infinity, okay? So some textbooks you might read and they will just leave it as does not exist. On the AP exam, they like the better description where you say infinity, okay? So, there is no limit, but we are going to give a description if we can. So let's go here. So our limit as x approaches 2, here's our target, from below. So this graph is going down. And one-sided limits, it is best to say that as well. 2 from above, well, those values are getting bigger. I like to write the plus just to emphasize it, but you don't have to write that positive, okay? Since these two infinities don't agree, we're going to say does not exist, okay? The function value at 2 is an asymptote, so that also does not exist. You could write undefined. I just write does not exist. All right, so let's look at example 7. 2 from below, 2 from above, -2, sorry. And since they both are going to negative infinity, they do agree. So we do have a limit, a better description. And the function value is 0. All right, so now we're going to have limits as we go to negative infinity. So negative infinity are your x values. So it says, hey, what are your y values doing when x is really small or the far left behavior? Well, it's growing. And positive infinity, remember those are x values. And so it's saying, hey, what's the right end of your behavior doing? Okay. So an example 9. All right, negative infinity would be the far left. And positive infinity is the far right. Now, these dotted lines are never really there. It's just a guideline for the graph, okay? They're trying to just kind of show you some patterns. So the limit of negative infinity, well, we're leveling off and we're getting close to 4. We have a horizontal asymptote. And then positive infinity, same thing. We're leveling off and that's -2. All right, now this, we've got negative infinity. And so what you notice is we start bigger and we're kind of getting smaller. And so that pattern's going to keep going. And so since my graph is getting smaller, we're actually going above and below, but we're getting closer and closer and closer to that distance being nothing. And so it's going to verge out on that asymptote, which is 1. And then the same idea here. These are getting smaller as well. And so it's just going to keep continuing that pattern until it kind of levels out. Oops. And it looks like it's almost on the axis, which is y equals 0. All right, number 12 is slightly different. So on the left, these we call this oscillating. They're going between 4 and -4 the whole way. Well, you can't have two values, so this does not exist. And as we go to infinity, these are getting smaller, and so they're going to get like smaller and smaller and smaller And so we can say infinity. So see, if your pattern doesn't decrease or converge, then it does not exist. If it does, then you follow the pattern. All right, you give yours a try and see how you do.